Logarithm is the inverse of an exponential function. All around us, logarithms are curving into infinity, gradually slowing down, but never giving up their hopeless dream of one day reaching infinity. Come with us on a journey and discover how properties of logarithms can help us solve derivatives. Our story begins in 1727 in Berlin, Germany, where a man named Leonhard Euler is hard at work doing math and stuff. He started using a certain constant for the base of logarithms, which he assigned the letter e. A surprising property of e is that e to the x is the only function which is its own derivative. The inverse log base e of x is also called the natural log. The derivative of this is 1 over x. Here is the proof. Through these surprising properties, nature has given us a shortcut to finding derivatives. At Columbia University in New York City, calculus students are hard at work using logarithms to find derivatives.
Good afternoon. My name is Richard. I'm here to discuss. As the introduction suggested, we are discussing logarithmic differentiation, and I'm going to go over the basic rules of logarithms so that we have them in mind while we're doing some of these examples. So as we just discussed, these are the basic rules of logarithms that we're going to be using to find some of the derivatives. I'm going to be doing the first example, which is y equals x to the x. So here we have y equals x to the x. And the first thing that we're going to do is we're going to take the natural logs of both sides. So we've got natural log of x to the x, natural log of y, right? Then based on the power rule that we discussed earlier, we know that the natural log of x to the x is going to be equal to x, natural log of x, and on the other side that's just going to stay the same, natural log of y. We shifted angles to get a better view. Hopefully this makes more sense now. All right, so now that we have the natural log on both sides, we're going to start taking the derivatives. All right, so derivative of natural log of y and the derivative of x times natural log of x times y prime equals x plus natural log of x. Now here, we're going to be using the chain rule, and here, we're going to be using the product rule, right? We're trying to get rid of y, and the way that we get rid of y is, since on this side it's being divided, right? You're dividing y prime by y, so you're going to have to multiply. So we do this to get rid of these, and then that's going to, well, this one doesn't, we don't end up getting rid of that one. That one stays. But this one disappears, so this ends up just being y prime equals y times 1 plus natural log of x. And then we just substitute that y for x to the x. So then the answer is y prime equals x to the x times 1 plus natural log of x.
In this video, we're going to be making reference to the product rule and the quotient rule. And it looks like there's two different rules for each name. This is the product rule of logs. Then we also have the product rule of derivative. And if you want to get the derivative of this, you do a of x times the derivative of b of x plus b of x times the derivative of a of x. Where's my eraser? Similarly, we have the two quotient rules. Again, the log quotient rule is the quotient rule of derivatives is but those are the difference. So if we refer to the logarithm rule or the derivative rules of products, quotients, try to use context clues.
So for this example, we're going to differentiate x to the sine of x. And we'll start by having it set to y. And then to bring the exponent down, we're going to take the natural log of both sides, like we did before. But that obviously comes down in the next step. So we can use our old tools where we have f or g and then f prime and g prime. And we have f as sine of x, and then g is ln of x. And g prime is 1 over x, and f prime is cosine of x. And then the next step we have is we're going to just plug that into our equation. So we have ln of y, and then product rule, which is sine of x times 1 over x plus cosine of x times ln x. Then we have to get rid of the y rational by multiplying both sides by y. But before we do that, we have to differentiate this side as well, and the differentiating ln is just 1 over y. And then we can get rid of this y, multiplying both sides. But we have dy over dx now, which equals y times sine of x times 1 over x plus cosine times x times ln of x. As we said earlier, our y value is still equal to our original function, so we just plug that in. We'll plug it back in, so x times sine of x times this, which is 1 over x plus cosine times x times ln of x.
Okay, so you can use the product logarithm rule if you're feeling lazy and you don't want to simplify stuff. So if we want to differentiate this, we don't really need to expand it if we want to use the product logarithm rule. So we can make this ln y equals ln x2 x plus 3, and using the product logarithm rule, this thingy here equals plus ln x plus 3. And then if we derive that, we can just use the derivatives of the logarithms. So in this case, we're going to have to use the chain rule. This over here is nice and easy. Equals, and then we want this to equal the derivative of y. Then we just sub back in for what y is, get it all in terms of x. And there you go. This isn't going to save you any real time in this example, but this is just a setup for future use. So you know that you can use the logarithm product rule to simplify derivatives. So you could derive this using the derivative quotient rule, but the derivative quotient rule kind of sucks and is a pain to use. So we're going to use the log rules to simplify this and avoid using the quotient rule. Using the quotient logarithm rule, we know that whatever all that is equals the natural log of sine x minus the natural log of that polynomial. Now we can take the derivative of both sides, and we know that the derivative of log something is the derivative of that inside part divided by whatever that part is called. It's the derivative of y. And we simplify to get all in terms of x again. And there you go, that's the derivative of a function like this, avoiding the derivative quotient rule by using the logarithmic quotient rule.
What we're first going to do, because this is logarithmic differentiation, that's the whole point of this video, we're going to take the natural log of every single expression, right? So we'll call this y. We'll call that y. So we get 9x to the third minus 14. Okay, now I ran out of space. So pause it and I'll like write it out up at the top and do that again. We're gonna take the derivative of this whole thing. We're gonna take the derivative of all of this. We're gonna treat y as a function, right? So this is the chain rule, meaning the chain rule structure, as we know, is the derivative of that would be the derivative of the outer function, and then you still have the inner function, but then you multiply this whole part by the derivative of the inner function, right? So first we're going to do the chain rule to derive this. The outer function is natural log, so 1 over x is the derivative of natural log. Okay, so I actually did this problem, but I made a small error. If you're wondering why the 6 is blue, it's because the first time I did this problem, I forgot to write it. So I'm going to just adjust that. Y prime is equal to 2x squared plus 3x times 4x to the 7th minus 3x divided by x squared plus 1 times 9x to the 3rd minus 14 multiplied by 4x plus 3 over 2x squared plus 3 plus 28x to the 6th minus 3 over 4x to the 7th minus 3x minus 2x over x squared plus 1 minus 27x squared over 9x to the 3rd minus 14. Thank you for watching.
The magnitude of earthquakes are logarithms. The pH of liquids are logarithms. The brightness of stars as they increase in size, logarithms. Even sound is logarithmic. Everywhere we look, nature seems to prefer the logarithm over plain old linear growth. In calculus, the natural properties of logarithms can help us find derivatives. And all you have to do is take the log of both sides. Thank you for watching.